So in this video we're going to cover topic number 52, which is the method of joints. Uh, so the method of joints utilizes this fact. So for our truss, we know that the entire truss, right, we are assuming the entire truss is in equilibrium. So because the entire truss is in equilibrium, we're going to make the assumption that each joint must also be in equilibrium for the entire truss to be in equilibrium. Alright, so since we in the last video we talked about that at each joint, all the forces will act at the same point. Therefore, no moments will develop. Alright, because of this, we can say that only the sum of all the forces in the x direction have to be equal to 0, and all the sum of all the forces in the y direction have to be equal to 0 to ensure our equilibrium condition. So when you're applying the method of joints, what you should do is you should start at a joint with at least one known force and at most two unknown forces. So in our truss here, alright, if we look at each joint, or we have three joints. We have joint C, we have joint A, and we have joint B. Alright, at A, alright, we have the force due to the member AB. Alright, we have the force due to the member AC. Alright, and then we have our two reaction forces. We have our reaction force AX due to the pin at point A. Alright, and then we have our reaction force AY. Alright, so at A we have four unknown forces. Alright, we have 0 known forces. So we cannot apply the method of joints at point A right now. So let's look at point C. Alright, so at point C we have the force due to within AC, which we'll call FAC. We have the force due to member BC, FBC, and then we have our reaction force due to the roller or the rocker at point C. So we'll have our normal force due to that here. Alright, so at C we have 3 unknown forces and we have 0 known forces. So we cannot apply our equilibrium equations here. So that what we are left with is the joint at B. Alright, so we're going to draw the free body diagram of joint B. Alright, so at B, if we look up here, we have a known force of 500 newtons. All right, and then we have a force of that goes along BC, FBC, and then we have a force FBA. All right, that'll go down. All right, now I'm going to redraw the arrow or the direction of FBC because I know that there is a 500 Newton force that's going along the positive x-axis, and then in order for this to be in equilibrium, the sum of all the forces in the x direction have to be equal to 0. So I'm going to say that force BC actually has to be going into the joint B in order to balance the 500 Newton force that's going along the x-axis. All right, so we know that FBC would be at a 45-degree angle with the y or the x-axis, so I'll include that here. And FBA would be going along to the negative y-axis. All right, so what I'm going to do is I'm going to redraw the free body diagram at B, but I'm going to include the members. So I'm going to draw our member BA. I'll include the force FBA, and then I'm going to draw our member that goes along BC. All right, and I'll include our 500 Newton force. All right, so the reason, and then we still have our 45-degree angle. All right, so what I'd like you to see here is you have if we look at FBA, you can see that it is pulling on our member here. All right, so this section here is supposed to represent member AB. All right, and you can see that it's getting pulled. The force BA is pulling on this member. Therefore, we can say that this member would be in tension. All right. Now, if we look at FBC, all right, this is supposed to represent member BC. You can see that the force is pushing on that member, or so we can say that that would be in compression, or that member would be in compression. All right. So if we look at our free body diagram, what we can say is that forces that are pulling on the pin, or they are coming out of the joint, what we can say here is that they are in tension. All right. While the forces that are going into the joint, or they are pushing the pin, all right, we can consider those to be in compression. All right. So using the free body diagram, you should be able to determine whether or not the member will be in tension or in compression. All right. So so to analyze an entire truss, what you can do is you can use the following analysis procedure. So you'll first draw the free body diagram of the joint with at least one known force and at most two unknown forces. You can then, by inspection or assumption, label the direction of the unknown forces on the free body diagram. You should then make sure to orient your x and y axes to most efficiently solve the equilibrium equation. You'll solve for the unknown forces using the equilibrium equation, and you can then determine whether or not the assumed sense of direction was correct. Alright, and then the last step would be to go to the next joint and then continue to solve for the unknown forces using steps 1, 2, 4. So you will apply the method of joints at each joint within the truss. Alright, so there's two methods which we talked about in step 2 of this process, where you can determine the direction of the forces within the truss. Alright, so the first method is to use the method of inspection. So if we looked at our last problem, we saw that there was, so I'm going to go back one page here in the handout, and what you can see is if we look at joint B, we know that for the sum of all the forces in the x direction to be 0, we knew that BC had to be going into the pin. There was no way it could counter the 500 Newton force if it was going out of the pin or going towards the bottom right hand corner of the page. So for that to be true, we knew that FBC had to be in compression in order to balance out that force. So that's the first method, or that's the so if you are unable to determine the direction of a joint, what you can do is you can just assume a direction. All right. If you assume a direction, all right, and you solve the problem, all right, what will happen? Two things will happen. All right. You'll either get a positive magnitude for your answer. This means that your assumed direction was correct. All right. Or you can get a negative magnitude. All right. If you get a negative magnitude, it's not the wrong answer. All it means is that the direction on your free body diagram was incorrect. Or you can think of it as if you had guessed the member would be in tension, it's actually in compression. All right. So the second way you can do these types of problems is that you can just make the assumption that all members in your truss will be in tension. All right. So you can then just solve your equilibrium equations at each joint. All right. And then what you'll find out is that if you make this assumption, all your positive answers would correspond with members that are in tension. All right, and then all your negative answers would be in compression. Alright, so that will conclude this video. We'll have a couple videos on some example problems on how to do these.